Kia ora, and welcome to Insol webinar presentation, presented by Chulo. In a moment, we'll introduce you to Greg Simmons, Chief Operating Officer and owner of Insol. Greg lives and breathes facade treatments and will guide us through the history of the business, his team, deliver some insight into a few of their projects, and get us up close and personal with Insol's signature wind tunnel. So let's get started.
Well, we're a family business. We kicked off in 2003 just focusing purely on louvers. We had a strong construction and manufacturing background within the family, which suits the area of the market we're working in quite well. We expanded from selling just louvers into any type of screening, perforated sheet metal or whatever it might be, to do sun shading or privacy screening, anything like that. We don't do windows or cladding. We don't do anything that deals with the E2, the weatherproof line of the building. It's just the screening elements. Around 2018, we cut off, or sold off, should I say, the residential part of the business. We also sold off anything to do with ventilation louvers, to air intake grills and things like that, which has really led us to a lot higher focus on the design and engineering. We do a lot of careful work around how the products are put together and how they perform. We do a bit of testing. It's really the primary thing that's led us to build ourselves our own wind tunnel testing facility. We find that the demand for the product and service we offer is largely driven by two things. High density living is driving needs for privacy requirements, for like screening of balconies. It's also driving the need for pleasant urban environments. The urban planning rules mean that you're not allowed to build a ugly car park now. You have to have some kind of architectural feature to make sure you've got a much more pleasant streetscape. Also for pedestrian comfort, things like canopies over, the facades need to provide some kind of shelter. And that's all largely driven by higher density living, and that only is going to increase. The other thing that's driving it is energy efficiency requirements for buildings. So you see the government is mandating requirements for Green Star ratings on buildings. That means they need solar shading. They want to reduce the solar energy ingress to the building, which means there's lower requirements for their HVAC, the air conditioning usage over the course of the building's life, reduces its daily energy use. So that's the key areas that or key drivers to the niche that we find in the market for these screening products. When an architect approaches us with a project, normally there's typically a bit of a life cycle it goes through, where you got the architects after technical assistance on how to achieve things. Then there's budget estimating. We've normally got one staff member handles most of that. There's two or three within that team. And then we've got design, it gets a whole lot further involved. Got several draftsmen and engineers in the design team that back up the technical assistance team. There's estimating for the builders, so when it gets into tendering. Then we have project managers who see a job through to completion, and also factory management to ensure that the product is manufactured properly. But how about we hear from some of them?
Hello, I'm Archie Simmons. I do sales and estimating here at Insol. I've been here for 3 years. My role involves assisting architects at the early stage of the design, so I provide them with technical data sheets and engineering details that we have here at Insol to influence the design at an early stage, and then as the design progresses, help to oversee the early design and engineering involvement that we have from the design team here at Insol. And then further down the track, I get involved during the estimation phase. So when the builder approaches us with a tender invitation, I take care of the estimating and quantity surveying. At the moment, we're working on a high-spec apartment project in Parnell. We've been involved for quite a few months now, assisting the architect with details and different ideas around how to make his facade work. He's looking at a facade with perforated and solid aluminium components arranged on various angles to create a shimmering effect on the building. As the project has progressed, I've also been involved in pricing the works for the main contractor, and with budget constraints that they're now facing, we're looking at different ideas to reduce the cost and some value engineering options. One thing I love about what I do here at Insol is I get to create beautiful facades and have a meaningful impact early on. I love being able to see the finished product on the building and know that I had an influence in that, and I helped turn the architect's vision into a reality.
I'm Bradley Murray. I play a lead design role here at Insol, and this is my 10th year with Insol. As a designer, I guess the main part of my role would be taking what the architect has designed, his architectural intent, and taking that through to a completed reality. So that would involve how the product's going to be fabricated, through to getting it engineered and right through to installation. Yes, our current project I'm working on at the moment is a block of apartments in Takapuna, Auckland. There was a bunch of product we had on there, and then there was also this nosing product that was running around the outside of the building on all levels, and the architect had originally designed it as a cladding panelling type product, and that got rejected down the track due to cost implications, and they engaged us to do a replica of this in a louver module that simplified the design quite significantly. The biggest part I love about my role is going through the headache and the pain and the pressure there is in pulling a project together, and then finally seeing it finished, installed on a building. It's probably where I get the most satisfaction out of my role here at Insol.
So my name's Vincent Murray. I've been working for Insol for 6 years, and I'm a project manager. My role involves getting the set of confirmed shop drawings and getting the products made and fabricated. This involves working closely with key suppliers and local fabricators. My relationship with them is key to our success and being able to produce project on time and in budget. One of our successes here at Insol is that we pull from a wide range of suppliers and fabricators, allowing us to spread our resource pool. This is critical for our success when running multiple projects. So the project I'm working on at the moment is University of Waikato. The PA consists of a range of custom fabricated chevron fins, which are fabricated from sheet metal. These have to be fabricated in a factory environment and then brought to site and craned onto the building. It also involves a range of louver sun shading elements. We've got vertical louvers are 640 mils deep and are fixed to the vertical side of the building to create sun shading. Also involved in this project is glass fins around a stairwell. We've custom built our own glass bracket system. Each panel of glass has got an inset fret in the glass. This project is due for completion later this year. We're already well into procurement of materials and getting samples fabricated for architects' approval. What I love about working at Insol and what I do is being able to see something tangible from the work we do, taking a set of drawings and actually seeing a finished product on the building. It's so rewarding, and it's there for years to come, and every time you return to that place you can say I had part in that, and it's just that feel-good factor.
Okay, my name's Tom. My main role is General Manager, and alongside of that I hold fabrication and procurement roles in our factory here. Yeah, I've been in construction-related industries most of my life, but this will be the longest role that I've held. And obviously I'm a director and I'm planning to stay. My role here at Insol in the fabrication side of things really heavily revolves around assisting the project managers to deliver their projects by the effective use of materials and resources, and in particular leveraging associated skill providers that we align ourselves with, which allows us to deliver complex and customised projects to a wide range of locations across New Zealand, and also in a wide range of sizes from small right up to high-rise complex projects. It's an interesting question what challenges we have. Everything is customised, and I mean everything is customised. So the profiles are customised, the colours are customised, the building is customised. There's varieties of elevations, there's varieties of technicalities, and then there's often a deliberate random aspect, because there's some features that are, these are architectural features, and so you will get a lot of challenges, and to be honest, that's part of the fun. 2 or 3 interesting projects spring to mind. Whether I'd call them favourites, I'm not sure, but they're definitely standouts. And one of them would be Ebbert's Holden, which is a project in Te Rapa in Hamilton. And it's quite unique in the sense that we fabricated the whole thing here. There was no CNC equipment used in the fabrication. Because we've got the scale in our workshop, we were able to lay it out and make sure there's no compounding errors, and package it, deliver it to site, fully powder coated, and it went together like a glove, and it looks really stunning now. Another one would be the Aotea project, which is only just recently finished, and that was a similar example where we fabricated large scale sections that were freighted to site. The last one that comes to mind as another recent project is Manurewa High School, which was random in the sense that it had multiple arches which were cut into the louvers, and some of them were I guess a parabolic arc, and they varied from one to another, or there were several different types, including a circular window, which was, when we're talking about challenges, that one was out there for challenges. Something I'd like to see happen more in the industry is a greater level of working together with skilled partners to provide a better solution that is not just silos where you're dealing with a contractor or a specialist in a particular thing, but you're dealing with a more complete solution. And I feel like at times we're an extension of the construction site, is that we're perhaps more involved in it from that aspect, and it means you have a greater interest in the methodology, and you can save money, you can save weight, you can save time, you can save scaffold costs, you can save health and safety. You can minimise the number of people on site for 1 week or 6 weeks or whatever it takes is a win-win. So one of the things I think customers appreciate about Insol is the fact that we will take on anything. I like to refer to a quote of, I think it's Richard Branson, and he says, say yes, then find a way. And I know that there's been many projects that we've successfully completed over a long period of time where when the opportunity arose, we didn't know how we would do it, but we were willing to give it a go, and we took it on and we found a way, and the projects that we're proud of now.
We find that our core competencies fall into three kind of separate zones that all overlap. Our first sort of zone of knowledge is in facade engineering and also in architectural intent. So we understand what the architects are trying to achieve when they give us a concept. We understand the look they want to get, and we understand their needs around compliance. We understand what they've got to do to get a building consent. And then we have an understanding of the engineering that goes into making, like bringing that intent to reality. And then we have another zone of knowledge is around construction methodology. It's all very well to draw something, but realistically, if you can't crane it onto site in that size, well, you need to make it more modular. So we understand how to make something in a way that can be easily and economically built. Our third area of knowledge is the manufacturing. We've got an acute understanding of all different areas of manufacturing that go into pulling this kind of thing together, from how things are extruded to the welding to the laser cutting. And you can take the efficiencies of knowledge from the manufacturing side, overlap them with your knowledge of construction needs and the architectural needs, but make something that complies. There's a lot of hidden things that go into it. What we find is that there's plenty of people with a lot of knowledge in one of those zones, or potentially even two of those zones, but it's rare for all three to fully overlap, which is where we bring a big difference to the table for the architects. There's a lot of people out there and companies that manufacture product. They'll manufacture anything, you give them a drawing, but they're not going to install it for you, and they don't understand how to make it comply. We've got to consider elements of the building code, might be B1 and B2, it's like structural and durability, or F4 is safety from falling. And sometimes our facade element might be privacy screening for a balcony, but it's also acting as a balustrade, so that it needs to be engineered to suit that part of the building code. All of that work requires a producer statement. So the council needs to see an engineered documentation that proves that what we've designed is going to comply, it's going to meet the code, and you've got to provide all the justifying calculations with it. So the compliance part and understanding the needs of the architect to get a consent, that's got a big part of that knowledge zone around the architectural and engineering part. So if what the architect has drawn is not complete in every detail, it might not stay on the building, or it might corrode too early, or whatever issues might come up that may have been missed out. Likewise, you get people that understand the building and buildability but don't understand the manufacturing side of it. End up building something that's much too heavy, much too expensive, just simply because they can't get the efficiencies out of how something might be manufactured. So really overlapping those three zones is where we provide a real value to all different parties, really, in the whole building construction team that's pulled together to bring a building to reality. We finished Aotea Square just late in 2021. It was a very challenging and very rewarding sort of a project. It's an interesting building. It's had a bit of a checkered history, I understand, built long before I was around, but some interesting history on the project, and it's been controversial for most of its life, and no doubt the current architecture will still be controversial. But from our perspective, it was a fantastic project. We did this long louvered ribbon, the architect called it, with a contoured geometry to it, which was the intent there was to was around the movement of a dancer, drawn from that concept as being to pull that through, because it's ultimately it's a theatre. But it also was backlit. We had to integrate lighting all the way through it, so it's a very interesting, challenging project. A lot of challenges came up for the architect and the engineer. The original proposed design was thrown out because of fire compliance issues, which is why they came to us for a louvered option. The structural support that needed to be drawn from the existing structure was very complex, fraught with interest, shall we say. And then value engineering, there was major budget problems. We had, it's the first project I've ever worked on where the roof was value engineered out. So they had an existing roof that had some waterproofing issues, but they were going to stick another roof over the top of it that concealed a lot of plant and things like that. They ended up literally value engineering the whole thing out and fixing the waterproofing on the existing roof instead, which was interesting. Like I say, first time I've ever seen the roof value engineered off a building. But right through all that, we adapted and changed our approach so that the architect's intent would come through. So one of the most challenging projects we've done was the Burwood Hospital project in Christchurch. Complete new build after the old one was damaged in the earthquakes. And the bulk of the project for us involved these big, tall fins. They were 1 metre deep, 8 metres tall, about 180 of them or so on the project, around about 1100 millimetre centres, so quite close together. And they also had fixed perforated horizontal sections in between them. When the builder brought it to us for pricing, we looked at the architect's details, and it was all drawn in solid, like a big heavy structural steel frame with this kind of subframe, top hat subframe underneath it, and then aluminium cladding on top of that, just an ACM panel cladding. And it really raised quite a bunch of sequencing issues in our minds, and it was also a very expensive way to do it. There's things like these steel frames needed to be welded to some weld plates in the wall, and you couldn't paint the wall or the welds or part of the structural steel frame. But you're working nearly 12 metres up to the top one. These things are only 1100 mils apart, and you're 1.2 metres off the building. You couldn't even get a lift in between them to get in there and do the painting you needed. So it was going to be quite a major sequencing issue with a lot of man hours and time on site to achieve it. We came up with a suggestion of let's do this in aluminium extrusion instead, where we'll bolt it to the plates in the wall, and the aluminium extrusion comes pre-finished to our factory. We cut it to size, clip it together. We have this big fin that's 75 mil thick by 1 metre deep, and we ship it to site, lift it into place with our special lifting jig, and bolt it off when it's done. So minimal man hours on site, just completely do it off site. And it was where the real challenges came in, were engineering it to ensure that it could handle the loads. One of the problems was that it was 8 metres tall. We couldn't fix it at the top because the top layer of the hospital had significant seismic drift requirements on it. The first fixing down below the top was 3.2 metres down, so we had a 3.2 metre cantilever on the top of this fin, and we had to prove that that would work, engineer it. After a lot of calculations and some physical tests, we proved that and managed to get this put in as an alternative. Ultimately, we saved the client over $1 million and cut about 6 weeks off the construction program, which really was where we brought our zones of knowledge to bear on that particular project and how we could help them achieve what was required in the architectural intent, but in a better way. So another project we've had completed fairly recently is the Les Mills car park building on Wellesley Street in Auckland. And that was a situation where the architect had spent quite a lot of time coming up with the concept of what they wanted it to look like, and they were battling with how do we achieve this. They'd done preliminary details that involved a big structural steel frame, fairly heavy, that gave them the depth and texture that they were looking for, because the whole facade was these diamonds that, the centre of the diamond was 300 millimetres out from the corner points. They designed this facade substructure out of sort of 100 by 100 structural steel, and then were fitting flat sheets to the front of that steel, and it was quite heavy, quite expensive, and quite labour intensive on site. And we had a look at it and suggested, well, we can actually get the depth you require here in folding the aluminium sheet back, which simplifies your structural steel significantly, and that it means it can just be in the one flat plane. We also suggested that if they put their verticals at 1.5 metre centres or less, that steel structure, which would act as the facade support, would also double as the vehicle impact barrier, and would meet the rules in the loading code. And that actually meant they could not only simplify their facade structure significantly, but also delete a lot of steel that they had included in the structure just for the vehicle impact requirements. And I think we saved 20 or 30% of the steel that they'd put into the building was just deleted. Then we came up with this panelised system with the depth folded into it, with quite a simple bracketing system off the vertical steel. We just dropped these panels in from the roof and fixed them off. Quite quick and simple process, with a lot of the grunt work being done off-site. So it was a fairly major achievement for us, quite challenging from the point of view of detailing and engineering, but really pleased with the result. The architect we certainly came up with a very tidy solution for the architect, and they were very pleased with it. And it was a much better solution from a building program perspective as well. There's two main reasons why we built this wind tunnel, or two main things that we need to look out for. One is wind noise, the other's structural stability. The wind noise one is a really tricky area. It's something that you could be using a product all your life, and it's never had caused a problem, but then there's one particular project where it does. They've been used for years, and then suddenly there's an example on a car park at the Northern Beaches Hospital in Sydney, 7 stories of car park with a fairly standard perforation pattern, and it just screamed. right next to a hospital was bad news. And poor old contractor had to fix it up. You just really don't want to go down the route of putting a nice facade on something like a hotel where people sleep, or a set of apartments, and risk that it will end up making this kind of, or some kind of noise. It's can be very dramatic. Some examples, if you wanted to research it, would be most recently there's an excellent one, the Golden Gate Bridge in San Francisco. They've recently replaced all the palings on the, like the balustrade on the pedestrian walkway of the bridge. You can hear it all over the bay. It's fantastic. The other thing is structural stability. So when I talk about that, I guess it goes for a wider range of problems. Mostly these problems focus on dynamic facades. So when I say dynamic facades, I mean they've got something that moves. They might be sliding screens or bifolding screens or pivoting screens. Making it move is actually the easy bit. It's controlling when and how it moves that becomes a whole lot harder. If you've got a sliding screen that gets caught by the wind and races off down its track, sort of worst, it could fall off the building because it's wrecked its wheels and fall down and hit somebody, potentially even kill somebody, or at best it's going to damage itself in some way. Certain types of mesh screen, there's just no way you can estimate what the friction of the wind would be going over the surface of it, and you just have to give it a 1-to-1 scale test. If you scale down your item and make it smaller and cheaper and easier to test, it's not going to give you the same results. It's different to trying to do a wind tunnel test to determine the loadings on a building, which is quite common. For this type of thing, you've got to have 1-to-1. With the bespoke nature of what we do, and the potential risks there are around failure due to structural stability or creation of wind noise and the issues that could cause, we decided it'd be a good idea to have our own facility on site so we can quickly and easily de-risk or mitigate the risks that are involved in some of the project work and the concepts that the architects are coming up with. This mock-up we've got here is a mock-up of a screen that we're going to be putting on some apartments in Auckland, around Herne Bay area. Now, it's just a very rough example for the purpose of testing, and what we were actually testing on it is this. There's a hardware latch item running up the side here. The reason for testing it is these screens slide, and when you've got a vertical element, vertical slats, they catch the wind quite a lot, and they can get a lot of speed up on the track and easily get damaged or even fall off the building. So we were testing this one to see at what sort of wind load it would fail. Let's see up here with the engaging pin is bent over and failed at about 20 meters a second, and the latch no longer works. So a bit of modification to make to that to make sure that the system's safety onto the building. So the building is a student accommodation building, big precast wall, 16 stories high, punch windows in it, and of course urban planning rules determine that you can't have a big ugly concrete wall like that. So the architect's got these nice window hoods that not only break up the wall and give it some interest, but they're also a bright yellow, and they put in some colour in there, give it some texture and colour. The client was worried that some window hoods were going to make noise or vibration, which would be irritating to the occupants. Now, we tested it this year. This wall is representative of this would be your precast concrete here, and this over here would be your window, and this is your window hood. This is one of two types that there were on that building that we needed to test for vibration and noise. Now, that obviously just went in front of the wind tunnel. We then rotate it on the turntable through 180 degrees at varying wind speeds up to 45 metres a second, and just to see whether there's any audible irritating noise or vibration coming out of it, and measure those elements as well. This example we've got on the turntable now is it's a custom dapple pattern. Dapple's our brand for perforated sheet metal, and in this one here the architect was interested in 8mm perforations at 12mm centres on the staggered pattern. Quite an interesting project with a very random series of fins off the face of the building. They're about 500 deep, these fins, right the way around the building and the full height, and out of this perforated material. The architect was keen on quite a fine sort of a mesh, which we were worried was going to make a noise. We advised that perhaps we should test it. So along with several other patterns, we've run some tests. Unfortunately, this one does make a bit of noise, and we'll run that up to show you what the noise is like. So it's bolted here on the turntable with just a simple mock-up frame that we use to hold things to. The wind tunnel set up here with the 3 metre by 3 metre nozzle in it. So the 4 big fans we've got can move up to 500 cubic metres of air a second, and it's normally through a 4 metre by 4 metre opening, meaning we can test some pretty large elements. That will take us up to about 115 km/h wind, and if we drop it to 3 metres by 3 metres with this nozzle, we take it out to 200 km/h. So we can pretty much hit anything we like with real world conditions and really test it. You might say that 200 km/h seems a bit ridiculous for wind speeds, but I'm telling you it's not. When you start looking at the factoring around the corners of buildings, 200 km/h that's quite real. So without further ado, I think we'll wind it up, I think. We're running at about 17 km/h wind speed at the moment, just a fairly gentle breeze. About to ramp that up to 36, 37 km/h, and at that point you'll start to hear this pattern, the dapple pattern here on the mock-up will start to make a whistle, which is quite noticeable. Any current whine you can hear in the background is part of the motor whine on the machinery at the moment, but the noise that this makes is quite distinguishable from that. Quite significant at relatively low wind speeds. I'd recommend for students to ask to visit manufacturing facilities, as many as they can, all the way down the supply chain. So just it helps to understand how things are made. It'd be one thing to come and visit a fabrication facility like ours, understand how things are put together, but then also take it further down the supply chain, go and visit a powder coating facility, understand how the aluminium is pre-treated and powder coated, and then again, if you can, visit an extruder. There's plenty of them in New Zealand, you'll be able to get one of them, and then if possible even go and visit the smelter. I know that's a whole lot harder. I don't think the smelter in New Zealand does tours anymore, but whatever material you're using, whatever it is, if you can't visit a manufacturing plant physically, I'd recommend or at least research how it's made and all the way down the supply chain, understand all the tensions and pressures that come into it. That's probably the key thing I'd recommend to improve your career. The key bit of advice I think that I'd hand on is that always try and understand things from first principles. A lot of what we have these days is kind of fed to us by a standard or fed to us by a bit of software, and a lot of it is garbage in, garbage out, or a lot of the standards are kind of one size fits all, and it's a bit, there's a lot of circumstances and situations where it doesn't apply, or if you understand things from the first principles, you can challenge those assumptions and justify being able to do something different, cooler, better. But you can realize visions that you may never have never had a chance to if you understand things from first principles, and you can challenge the norm, and try and work with other people who do. Find other people and develop a network of other people that understand things from first principles.